Section: Introduction. In this section, we discuss the rise of transformer-based foundation models in sequential modeling tasks across various machine learning fields. These models excel at processing sequential data by understanding long-range dependencies and temporal relationships. Their effectiveness is particularly notable in areas like natural language processing, time series forecasting, and speech recognition, where recognizing sequential patterns is essential. One of the main advantages of transformer models is their ability to learn from vast datasets, often containing millions of examples. This capability allows them to tackle complex tasks with larger model sizes, reaching up to billions of parameters. In autonomous driving, transformer models have shown significant success in behavior modeling, which involves predicting the future actions of traffic agents to aid in planning and motion prediction. Unlike traditional methods that depend on manually crafted features or specific rules, transformers can learn the underlying patterns of agent behavior from extensive multimodal data. While scaling up model and dataset sizes has been crucial for advancements in text prediction, it remains uncertain if these trends apply to behavior modeling. Previous research often faced limitations due to the size of training data or model parameters. In our study, we conduct a thorough investigation into increasing data sizes and model parameters in the context of autonomous driving. We train a transformer-based autoregressive behavior model on over 100 million high-quality human driving examples, which is about 50 times larger than existing open-source datasets, and we scale the model to over 1 billion parameters, surpassing current behavior models. As we increase the amount of training data and model parameters, we notice enhancements in both quantitative metrics and qualitative behaviors. Notably, larger models trained on diverse datasets are better equipped to manage rare or edge case scenarios, which are often challenging for autonomous vehicles. This suggests significant potential in scaling behavior models to enhance the safety and robustness of autonomous driving systems. Our main contributions include the introduction of DriveGPT, a large autoregressive behavior model for driving, achieved by expanding both model parameters and real-world training data. We establish empirical scaling laws for driving behavior models concerning model parameters, data size, and computational resources. We validate the benefits of increased training data through scaling that covers 2 orders of magnitude and compute scaling that spans 5 orders of magnitude. Our experiments show that autoregressive decoders scale better than one-shot decoders. We also conduct quantitative and qualitative comparisons of models from our scaling experiments to confirm their effectiveness in real-world driving situations. Furthermore, we demonstrate our model's generalizability on the Waymo OpenMotion dataset, where it outperforms previous state-of-the-art models in motion prediction and achieves better results through large-scale pre-training. In the realm of behavior modeling, we recognize it as a vital task in autonomous driving, encompassing planning, prediction, and simulation. By utilizing multimodal inputs, such as agent history and map data, behavior models forecast the future states of traffic agents by analyzing their dynamics, interactions, and environments. Transformers have become popular in this area due to their ability to integrate multimodal inputs and model long-range temporal relationships. Despite the success of transformers, existing research often faces limitations due to the size of model parameters stemming from insufficient training data, which restricts the full scaling potential of these models. In our work, we expand our transformer models to include billions of parameters by training on a large-scale dataset of over 100 million driving demonstrations, validating the scalability of transformer-based models in autonomous driving. Large transformers have shown remarkable success in sequential modeling tasks by increasing model parameters and data sizes. These scaling laws have advanced various tasks, including natural language processing and speech recognition. While some studies have explored the scalability of behavior models in motion prediction and planning, they are often limited by data size or focus on a narrow range of scaling, making it difficult to draw significant conclusions. Our paper aims to investigate scaling properties regarding model parameters, data samples, and compute across a broader spectrum than previous studies. We specifically focus on an autoregressive decoder architecture that has proven to be both scalable and effective in generating accurate trajectories for traffic agents. Although there is some literature on large transformer models for robotic tasks, these models often differ in input features and environments, making them less applicable to driving tasks. Section Summary. In this section, we discuss the growing importance of transformer-based models in sequential tasks, particularly in autonomous driving behavior modeling, where they excel at predicting traffic agent actions by leveraging large datasets. We highlight our contributions, including the development of DriveGPT, a large autoregressive behavior model trained on over 100 million driving examples, which demonstrates improved performance and scalability compared to existing models. Section: Behavior Model. In this section, we describe our behavior model, which utilizes a standard encoder-decoder architecture. We employ transformer-based models for both the encoder and decoder because they are effective for sequential tasks. We frame our problem as predicting the future positions of a target agent over a specified time horizon. We do this by applying the chain rule at each step, using context information and historical positions of the agent. The context includes the target agent's past states, nearby agent's past states, and map information. Historical data consists of agent positions from previous time steps, which we use to predict the agent's position at the current step. We define a state as a complete kinematic state, including position, orientation, velocity, and acceleration, while position refers to the two-dimensional coordinates. Our scene encoder follows a standard transformer architecture that combines all input types into scene embedding tokens. It processes raw input features, normalizing them to focus on the target agent's perspective. Each input vector is transformed into a token embedding, and we use self-attention to create a set of encoder embeddings that summarize the driving scene. For the trajectory decoder, inspired by large language models, we use a transformer architecture to predict the distribution of future agent positions. The decoder converts agent positions into embeddings and, at each step, uses these embeddings along with the encoder's output to predict the next position. The output consists of discrete actions represented as Verlet actions, which help us estimate smooth trajectories. During training, we implement teacher forcing by using actual future positions as inputs for the decoder, allowing us to predict all future steps simultaneously. We apply a cross-entropy loss to measure the accuracy of our predicted actions against the ground truth. In the inference phase, we follow a standard approach by generating a trajectory over the time horizon in an autoregressive manner. We predict the action distribution for the next step, sample an action, and incorporate it back into the input sequence. We also sample multiple trajectories to approximate the distribution and refine our results. Our scaling experiments aim to understand how model and data size impact behavior prediction performance. By examining scaling laws similar to those in large language models, we can identify valuable directions for future research. We have curated a large-scale driving dataset from extensive real-world driving demonstrations, focusing on diverse scenarios and geographic regions. We scale our model size significantly, testing various learning rates and training each model for one epoch. We evaluate performance using validation loss, which serves as our main metric, alongside additional driving-specific metrics. Section Summary. In this section, we describe our behavior model using a transformer-based encoder-decoder architecture to predict future positions of a target agent based on historical data and driving context. We also outline our training and inference processes, scaling experiments, and the creation of a large-scale driving dataset to enhance model performance across various scenarios. Section: Data Scaling. In this section, we summarize our findings on data scaling. Our smallest dataset, containing 2.2 million samples, is similar in size to the Waymo OpenMotion dataset, which has around 44,000 scenarios with multiple agents. We also examined subsets of our internal dataset to analyze how data scaling affects performance across various dataset sizes. Our experiments utilized approximately 50 times more data than the Waymo dataset, allowing us to explore new areas in our design space. The results show that as we train on more unique data samples, performance improves, regardless of the model size. To enhance our best loss by 10%, we would need an additional 200 million training examples, while a 20% improvement would require about 900 million more examples. Thus, we conclude that data remains a key limitation for enhancing driving performance. Additionally, our scaling results are consistent across different model sizes, suggesting that we can make valid comparisons with smaller models beyond 10 million parameters. Next, we investigate model scaling across a range of sizes, from 1.5 million to 1.4 billion parameters. We increase model size by adjusting the hidden dimensions of transformers, finding that changes to other parameters, like the number of attention heads, do not significantly affect results. We observe that training larger models is sensitive to learning rates, so we conduct multiple experiments at various rates to find the best performance. Our results indicate that for a fixed dataset size, increasing model parameters improves validation loss up to 26 million parameters, after which it plateaus until 163 million parameters. While this differs from findings in large language model scaling literature, we note that actual driving metrics continue to improve as the model scales. Further research is needed to understand the differences between loss and metric measures in behavior prediction versus text prediction tasks. In our compute scaling analysis, we examine how compute, measured in floating point operations, flops, impacts training loss. We identify a decreasing boundary that shows the lowest training loss for the current compute value. As we increase compute, training loss generally decreases, initially steeply, then more gradually at higher flop values. This trend aligns with observations in the large language model scaling literature. We also explore the optimal combination of model parameters and data size for a fixed compute budget. Given the high computational costs, it's crucial to utilize our data effectively. We fixed the compute budget across different flop groups and found that a larger compute budget leads to better performance, with the optimal model size increasing accordingly. Our results indicate that data is the main bottleneck, as the smallest model size performs best at the largest flop groups. We also conducted an ablation study on two different decoder architectures, scaling our autoregressive decoder and a one-shot decoder by 2 orders of magnitude. The one-shot decoder uses a transformer to generate full trajectory rollouts at once, while the autoregressive decoder produces trajectories step by step. Our results show that, despite poorer performance at smaller scales, the autoregressive decoder scales better and outperforms the one-shot baseline beyond 8 million parameters. While scaling the one-shot decoder proves more challenging, we confirm that our autoregressive decoder can scale up to 100 million parameters in prediction accuracy, and we plan to investigate the one-shot decoder's scalability further in future work. Finally, we present detailed results of DriveGPT in planning tasks using our internal dataset and motion prediction tasks with an external dataset. These results further explore the impact of scaling and help contextualize our findings in driving tasks and metrics. Section Summary. In this section, we analyze the effects of data, model, and compute scaling on performance, finding that data remains the primary bottleneck for improving driving metrics, while larger models show mixed effects on validation loss. Our experiments indicate that optimal performance is achieved with increased compute budgets, and we demonstrate that our autoregressive decoder outperforms the one-shot decoder at larger scales, confirming its better scalability. Section: Internal Evaluation, AV Planning. In this section, we focus on our internal evaluation of autonomous vehicle, AV, planning. We train our model using a large internal dataset that includes millions of high-quality human driving examples. Our approach involves predicting the next action in a sequence to generate AV trajectories. To better understand different possible behaviors, we sample multiple trajectories, even though the AV will ultimately choose one for planning. We assess our planning performance using standard geometric metrics like minimum average displacement error, minimum final displacement error, and miss rate, as well as semantic metrics such as off-road rate and collision rate. We normalize these metrics across experiments to highlight performance changes as we adjust data size and model parameters. For data scaling results, we compare our DriveGPT model with 26 million parameters, which is close to optimal, trained on datasets of varying sizes. We use a baseline dataset of 2.2 million samples, similar to typical behavior modeling datasets. Our findings show that training on larger datasets significantly enhances the quality of predicted AV trajectories, particularly in terms of off-road and collision rates. We provide qualitative examples to illustrate this, showing that our model trained on 120 million samples produces safer and more compliant trajectories compared to one trained on just 2.2 million samples. In terms of model scaling, we train 4 models using our 120 million internal dataset, with the 8 million parameter model as our baseline. We observe that as the model size increases, performance improves across all metrics, particularly in collision rates at 163 million parameters. Although validation loss stabilizes between 26 million and 163 million parameters, driving metrics continue to improve, indicating that adding more parameters can enhance performance. We present an example where the larger model produces better trajectory samples that stay within road boundaries during a right turn. For closed-loop driving, we demonstrate the effectiveness of DriveGPT as a real-time motion planner. The model uses input from an industry-level perception system to navigate through challenging urban traffic scenarios. We show examples where DriveGPT successfully generates smooth and safe trajectories around obstacles. In our external evaluation for motion prediction, we assess DriveGPT on the WOMD task and explore the benefits of pre-training on our internal dataset before fine-tuning on the smaller WOMD dataset. We utilize the open-source MTR encoder to improve reproducibility and leverage its data loading capabilities. We make minor adjustments to DriveGPT to align with WOMD semantics and kinematic features. For validation results, we measure performance using standard WOMD metrics across different time horizons. We compare our method against the state-of-the-art MTR model. Our results indicate that DriveGPT outperforms MTR in all geometric metrics, especially at shorter time horizons. While we achieve lower mean average precision scores due to limitations in probability estimates, we note improvements from pre-training on our internal dataset, even with significant distribution shifts. We also report similar improvements in predicting pedestrians and cyclists, confirming the generalizability of our method across various agent types. Section Summary. In this section, we detail our internal evaluation of the AV planning model, which is trained on a large dataset of human driving demonstrations to generate safe and compliant trajectories. We demonstrate that increasing both data size and model parameters significantly enhances performance across various metrics, including collision and off-road rates, and we validate our approach through external evaluations on the WOMD motion prediction task, where our model outperforms existing benchmarks. Section: Data Scaling in Pre-Training. In this section, we validate the effectiveness of data scaling by pre-training DriveGPT on different sizes of our internal dataset. The results show that using more unique samples during pre-training leads to improved performance in the fine-tuned model, which aligns with our earlier findings that data scaling enhances model performance. For our test results, we present data from the WOMD test set, demonstrating that our method surpasses existing top non-ensemble models in geometric metrics. Specifically, compared to Waveformer and Motion LM, which utilize ensembles of up to 8 replicas, our model achieves the best minimum average displacement error and minimum final displacement error metrics, as well as the second best miss rate, all without any ensembling. We note that our method shows lower soft mean average precision scores due to less accurate probability estimates, as discussed previously. Consistent with earlier results, we see additional improvements from pre-training on our internal dataset. In our qualitative comparison, we illustrate that DriveGPT generates better trajectories in terms of diversity and accuracy compared to MTR. This enhancement is particularly noticeable in challenging situations with limited agent history and multiple possible future outcomes.